Good afternoon, ladies and gentlemen. My name is Andrew Karpenko, and I am going to talk to you about embedded microcomputer systems, which is also a course I'm taking at the University of Washington. So, first I'm going to talk about some of the technologies we're using in this course, and then I'll talk about what we're doing with these technologies. So the first technology is the AR drone by Parrot. And what this is basically a helicopter with 4 rotors. It's a quadricopter. It has 4 little microprocessors in it, which allow it to be completely internally stabilized, which means if you take off, it will hover in air without needing any control input. It also has front and down-facing cameras, which will be important further on. So the next thing we're using is the Make platform, and basically this consists of Make controller kit and an ARM7 processor. So the controller kit is a printed circuit board that has some headers on it, which allow you to easily connect wires and just write code for the ARM7 processor. So the ARM7 processor features 48 megahertz clock. That's how fast it is, and it has 256 kilobytes of memory. Basically, it is as fast as the computers built in the 1990s, and it's about 20 times slower than the current generation of iPhones. The next piece of technology we're using is a development board that was given to us by the electrical engineering department at the University of Washington, and this features the Make controller kit. It also has a breadboard on it, an LCD screen, a keypad, a speaker, and a motor. So what exactly are we doing with these projects? Well, we have, what are we doing with these technologies? We have 4 projects over the course of a 10-week period, which is just a quarter. The first one we do in groups of 2, and the next 3 we do in groups of 4. So let's dive right in. The first project was an introductory type project, which we basically looked at the Make controller as well as the C programming language. And once familiar with it, we flashed some LEDs on the controller at different frequencies, and we displayed some text to the LCD screen. The next lab, which also all these labs are built upon each other, so whatever we implement in the previous, we built upon in the next. So in the second one, we actually implemented an operating system that allowed us to run multiple tasks at the same time. So the 3 tasks that we implemented for this lab were reading values from analog sensors, and then also reading values from digital sensors, so those based on 1s and 0s, as well as the next task. The second task was driving a motor using pulses, as well as driving it based on up to certain speeds based on values gathered from the analog sensors. And the last task was outputting all of this information to the LCD screen. So lab 3 was even more advanced than the other ones. And for this one, we implemented FreeRTOS, which is a real-time operating system. And what this system allows us to do is to guarantee that certain tasks will finish in a certain amount of time, which is something in contrast to like Microsoft Windows or Mac OS X, which did not have any time guarantees. So the 3 tasks that we added during this stage were pulse width modulation, which allowed us to better control the speed of the motor, and it's a technology that's used for controlling and dimming the brightness of LEDs. The next task was interrupt service routines, and this allowed the processor to take action based on changes in the sensor value, as opposed to always having to look at the sensor value. And the last task was actually controlling the drone and getting it to fly, and we did that by reading commands or reading values from the keypad that's on there, and then generating commands based on that. So the lab that's still left is the 4th lab, and it's basically manual and autonomous control of the drone. And for that, we still have to implement the manual control stage. We have to build a better controller, then implement some algorithms for autonomous control. And so let's look at the manual control portion. The quadrotor has four blades on it, 4 rotors that spin in clockwise and counterclockwise. And basically, to change what the quadrotor is doing, you change the speed of the motor. So in this diagram, the green arrows indicate a certain speed that's required for the quadrotor to maintain its altitude. So then the red ones are the ones that you speed up, and the blue ones are the rotors that you slow down to get it to perform certain actions like roll, pitch, or yaw, or whatever. And then you can combine these different factors to perform more advanced maneuvers. So we communicate with the drone through Wi-Fi and Ethernet, and basically the drone acts as a router and gives out IP addresses to any devices that connect to it. So there's 3 ports that the drone communicates over, and these ports are UDP, which basically means that it's fast communication, but it is not guaranteed to arrive at its destination, which is important later on. So you can send commands to the drone over one port. Another port allows you to get video from the drone, and a third one allows you to get the navigation data from the drone. So then what are these commands that we're sending to the drone? Well, we already implemented the basic directional commands, which are like forward, back, left and right, rotate and whatnot. What we still have to do is implement the command structure that allows us to send all of the parameters in one command. So this would allow us to do things like back up the drone while it's rotating and going up at the same time. There's another scheme for controlling this drone, and it's basically to control the individual speeds of the motors. And remember I said that the protocol we're using is UDP, and it does not guarantee that messages arrive at their destinations. So this is why it is very dangerous to actually control the speeds directly, because if a command doesn't get to the drone, we don't know what it's going to do. So the last thing we're implementing is the controller for the manual control portion, and what we're using is the V Classic controller, and this uses the I2C interface, which is inter-integrated circuits. It's a communication protocol that's used by little microprocessors. So we'll be implementing these basic controls on the controller to control the drone. And remember how I said that the drone has it's an augmented reality drone. Basically what this means is that it has computer vision on it, and it can detect it can detect other drones in the air, as well as identify them and tell how far they are apart. So this is used for like augmented reality games on the iPhone and iPod Touch platforms. So the autonomous control portion of our project is based on using or following this path that's given to us. So we have to take off, get to 1 meter height, follow this path around target B and around target A, and then change heights in the middle of it, and then get back to the same starting point. And the closer we are to the starting point, the more points we will have at the end. So what is our approach to solving this problem? Well, we basically we don't have one yet, but we definitely plan on using computer vision and figuring out where we are on the path, trying to estimate that position once again from the computer vision, as well as some velocity figures that we can get from the drone. And we also plan to use a closed loop controller, which will basically take in an error signal and figure out what to tell the drone to do. And of course, since this is we're still working on this project, we might figure out a different solution as well. So in summary, we looked at the AR drone by Parrot, we looked at the Make platform, the development board, some of the projects that we did, the first 3, the introductory ones, and we looked at the 4th project, which is still needs to be done, and that consisted of manual control, autonomous control, and display. So once again, my name is Andrew, and we talked about embedded microcomputer systems. And does anyone have any questions?